You want to know what happens if you go at the speed of light? Well, let's think about it. First of all, you can't. You can't go at the speed of light. Not if you have any mass at all. We've been through this before. The closer you get, the more energy it takes. And to actually reach it, you'd need infinite energy, which you don't have. But suppose, just suppose, we ignore that little problem for a minute. Suppose somehow you could go that fast. What would you see? What would happen to time? What would the universe look like? That's the interesting question. And the answer is strange. Very strange. Let me start with something simpler first, something we can actually understand. Suppose you're on a train, not going at the speed of light, just going fast. Say half the speed of light, which is already ridiculously fast, about 150,000 kilometers per second, if you could do that. Now you look at your watch. Does it run slow? No. Your watch runs perfectly normal, 1 second per second, exactly as it always does. You don't feel any different. Time doesn't feel slow to you. But, and here's the thing, somebody watching you from the ground, standing still at the train station, they look at your watch, and to them, your watch is running slow. Not a little bit slow, a lot slow. At half the speed of light, your watch is running at about 87% speed. For every second that passes for them, only 0.87 seconds pass for you. Now, which one is right? Is your watch really running slow, or is theirs running slow? Both. That's the answer. Both are right. There's no absolute time, no cosmic clock ticking away the same for everyone. Time depends on how fast you're moving relative to someone else. This is what Einstein figured out. And it's not philosophy. It's not interpretation. It's measurable. We've tested it. Put atomic clocks on airplanes. Fly them around. Compare them to clocks on the ground. They're different. Exactly the amount relativity predicts. Okay, so that's at half light speed. Time slows down, but not too much. You can still function. You can still think. You're still experiencing time, just differently than someone watching you. Now let's go faster. 90% of the speed of light. Now things get more dramatic. Your watch, to someone standing still, is running at about 44% speed. For every second they experience, you experience less than half a second. But again, to you, everything seems normal. You don't notice anything weird. Your heart beats normally. Your thoughts proceed normally. It's just that, relative to the outside world, you're in slow motion. And here's something else. Distances contract. The space in front of you, in the direction you're moving, gets compressed. If you're heading toward a star that's, say, 10 light years away, and you're going 90% of the speed of light, to someone on Earth, it'll take you about 11 years to get there. But to you the distance isn't 10 light years, it's shorter, about 4.4 light years. So the trip takes you only about 5 years of your own time. The universe literally gets shorter when you move through it fast. Now this sounds crazy, I know. How can the distance be different for different people? But it is. This is what the universe actually does. Space and time adjust to keep the speed of light constant for everyone. All right, let's keep going. Let's push this to the limit. 99% of the speed of light. Now your watch is running at 14% speed. Time has slowed way down. The universe in front of you has contracted dramatically. 99.9%. Your watch, 4.5% speed. The universe, compressed to a tiny fraction of its normal size. 99.99%. Now we're at about 1.4% time flow. For every year that passes on Earth, you experience about 5 days. You can see where this is going. The closer you get to the speed of light, the slower time runs for you, and the more space contracts. And at the speed of light itself, well, let's think about it. At exactly the speed of light, time dilation becomes infinite, which is a fancy way of saying time stops completely. Zero time passes for you. And length contraction also becomes infinite. The universe in front of you compresses to zero distance. So, if you could somehow travel at the speed of light, from your perspective, the trip would take zero time. You would arrive instantly, no matter how far you were going. A photon leaving the sun and hitting your eye 8 minutes later, from the photon's perspective, it's instant. It's emitted and absorbed in the same moment. No time passes at all. That's what it means to go at the speed of light. Time stops. The universe collapses to a point in the direction of your motion. But now wait a minute. If time stops for you, how can you even experience anything? How can you think? How can anything happen? You can't. That's the point. You can't go at the speed of light because you can't experience zero time. You can't exist in a state where no time passes. That's not a thing you can do if you're made of matter. Only light can do it. Only massless particles, because they don't experience time. They don't have a reference frame where they're sitting still. They're always moving at light speed. They're emitted and absorbed, and from their perspective, if they had a perspective, which they don't really, it's instantaneous. Okay, but let's play with this idea a little more. Suppose you're on a spaceship, and you're going, I don't know, 99.9999% of the speed of light. Not all the way, but very, very close. What would you see? Well, first, everything in front of you would be blue shifted. Light coming toward you would be compressed, higher frequency, blue, ultraviolet, X-rays. The faster you go, the more extreme this gets. And everything behind you would be red shifted, stretched out, lower frequency, red, infrared, radio waves. But there's more. The stars in front of you would appear to crowd together because of aberration. Light that's coming from slightly off to the side would appear to be coming from more directly ahead. So stars would cluster in front of you. And behind you, they'd spread out and dim. At high enough speeds, most of the sky would be dark. All the light would be concentrated in a bright spot directly ahead of you. And time outside your ship would be running fast, very fast. If you're going 99.9999% of light speed, every second for you corresponds to about 2,000 seconds for the outside world. You could travel to a star 100 light years away, and to you, the trip might take a few months. But when you got there, 100 years would have passed on Earth. You'd arrive in the future. Not your future, their future. You'd be a time traveler, forward only, one direction. This is real. This is actually what would happen. We know this because we see it with particles and accelerators. Muons created in the upper atmosphere by cosmic rays. They shouldn't reach the ground. Their lifetime is too short. But they're moving close to light speed, so time slows down for them. They live longer. From their perspective, the atmosphere is thinner. They travel less distance. Either way, more of them reach the ground than should, and we detect them. Now here's something that bothers people. You're on the spaceship going 99.9999% of light speed. I'm standing still. To me, your time is slow. Your clock is running at 1/20,000th speed. But from your perspective, you're standing still. I'm the one moving backward at 99.9999% of light speed. So to you, my clock should be running at 1/20,000th speed. So which is it? Who's really slow? Who's really fast? Both. Again, both. There's no absolute answer. You see me running slow. I see you running slow. And we're both right. But how can that be, people ask? That's a contradiction. No, it's not. Because for us to compare clocks directly, one of us has to change speed. One of us has to accelerate to meet the other. And whoever does the accelerating, that's the one who ends up younger. That's the one whose clock actually ran slower in some absolute sense. This is the twin paradox. One twin stays on Earth. The other flies off at near light speed and comes back. When they reunite, the traveling twin is younger. Not by much if the trip was short, but noticeably if the trip was long enough. The asymmetry comes from the acceleration. The one who accelerated is the one who aged less. That breaks the symmetry. That's why it's not really a paradox. But anyway, I'm getting off track. The point is, time slows down when you go fast, and at the speed of light, it stops entirely. Now what about your mass? People say your mass increases as you go faster. Is that true? Well, sort of. It depends on what you mean by mass. There's rest mass. That's the mass you have when you're sitting still, and that doesn't change. An electron has the same rest mass whether it's sitting still or moving at 99.9999% of light speed. But there's also relativistic mass, which is a way of saying the faster you go, the harder it is to push you faster. Your inertia increases. You resist acceleration more and more. Some people don't like the term relativistic mass. They say it's confusing. They prefer to just talk about energy and momentum, which is fine. The point is, the faster you go, the more energy it takes to make you go even faster. And as you approach the speed of light, the energy required approaches infinity. That's why you can't reach it. Not because there's a wall, not because something physically stops you, but because the energy requirement becomes infinite, and you can't have infinite energy. Light can go at light speed because photons have zero rest mass, so there's no inertia to overcome. They just are at light speed, always, from the moment they're created. Let me try to explain this another way. Maybe it'll make more sense. You're always moving through space-time at the speed of light, always. Everyone is. Everything is. But that motion is divided between space and time. If you're sitting still in space, all your motion is through time. You're aging at maximum speed, 1 second per second. But if you start moving through space, you have to borrow some of that motion from the time direction. So you move through time more slowly. You age more slowly. The faster you move through space, the slower you move through time. And there's a limit. You can't move through space faster than light speed because that's all the motion you have available. You can't borrow more than 100% of your motion. You can't go beyond the total amount of motion through space-time that you have. At light speed, all your motion is through space. None is left for time. Time stops. You don't age. You don't experience anything. You're frozen in time. This is a useful way to think about it, but it's still just a picture. The real answer is in the mathematics, the Lorentz transformations, the equations that tell you exactly how time dilation and length contraction work. And those equations have a limit. That limit is the speed of light. And at that limit, things go to zero and infinity in ways that make it clear you can't cross that boundary if you have mass. All right, so let's come back to the question. what happens at light speed? From your perspective, nothing. You don't exist at light speed. You can't get there. You can get arbitrarily close, but not there. But from the perspective of light itself, if a photon could think, which it can't, but if it could, it would experience no time. It would be created and destroyed in the same instant. The entire history of the universe, from the photon's perspective, is instantaneous. Think about that. A photon created in the sun 8 minutes ago arrives at your eye. From your perspective, it traveled for 8 minutes. From the photon's perspective, no time passed. It was created and absorbed in the same moment. The sun and your eye are the same place from the photon's perspective. That's what zero time and zero distance mean. The entire trip happens instantly. The universe in the direction of motion has no length. This is hard to wrap your mind around, I know. It's hard for me too. Even after working with this stuff for decades, it still feels strange. But that's because our brains evolved to deal with objects moving at human speeds, miles per hour, tens of miles per hour, not 186,000 miles per second. We don't have intuition for that. We have to learn it, work with it, calculate it, test it, and then slowly it starts to make sense. Not intuitive sense, but mathematical sense, logical sense. And that's as close to understanding as we're going to get. So, final answer. What happens at light speed? If you're a photon, nothing. You don't experience time, you don't experience distance, you're created and absorbed instantaneously. If you're anything with mass, you can't get there. The closer you get, the more energy it takes, and you can never quite reach it. You can get to 99.999999% and keep adding nines, but you can't get to 100%. And that's not a limitation of technology. That's not something we'll solve someday with better rockets. That's a fundamental property of space-time. The speed of light is the maximum speed because it's the speed at which causality propagates, the speed at which now becomes then, the speed at which information travels. You can't go faster because there's nowhere faster to go. The structure of space-time itself prevents it. And if you could somehow violate this, if you could go faster than light, you'd break causality. You'd be able to send signals into your own past. You'd create paradoxes, effects before causes. The universe doesn't allow that. So the speed of light isn't just fast, it's the speed limit of reality, the boundary between what is and what can't be. And at that boundary, time stops, space disappears, and only massless particles can exist there, eternally frozen in an instantaneous moment that never ends because it never begins. That's what happens at light speed, which is to say, from our perspective, looking at it from the outside, something very strange. And from the perspective of light itself, if it had a perspective, nothing at all.